Hello and welcome to another video. In this video we're going to be working on trapping rainwater 2, and this one you have a n by n matrix and called height map, representing the height of each unit cell in a map. Return the volume of water it can trap after raining. So it's kind of hard to see in these pictures like how you figure out the water. This one's a little bit more obvious. I mean, you don't really see the heights here, I guess, but essentially yeah, the trick to this problem is figuring out, like, okay, if I have a cell, like, how much water can it hold? And so I wanted to show this example because and I would recommend doing the first, trapping rainwater, but in the first, trapping rainwater, because water can only go basically left and right, for a cell, all you really have to know is, like, what's the biggest wall to the left and to the right, and then all of that area will get filled up by water. So essentially, if I have, like, two walls here, I'll say I have some cell here. Like, the rest of this kind of doesn't matter. Like, whatever's in between doesn't really matter. If I'm just looking at this cell right here, like, all of this will get filled up to the height of this. So the height that gets filled up for this cell is this thing, regardless of what's here and what's here, as long as everything else is smaller than, like, the two biggest walls. But for this kind of problem, it doesn't really work. So you can't just say, like, oh, and one more small thing. So if let's say, like, this wall is taller than this wall, the water will fill up to this level, right? So essentially it will fill up to here if this was, like, only one dimension. But in this case, it doesn't really work like that. Like, I can't just say, like if these are my numbers, I can't just be like, well, the biggest wall up here is 13, the biggest wall here is 13, biggest wall here is 13, biggest wall here is 13, so the water here will fill up to 13. Because this is actually smaller than 13, so water can go out this way as well. So actually, once this fills up to 12, everything else will spill out. If that makes sense, because essentially, you want to look at, actually, it might even be less. No, it wouldn't. Yeah, so essentially that's kind of how it works. Like it would be easier to see, like, an extreme case. Like, let's say this is 1 and 1. Now, yeah, now, like, anything once this gets up to 8, anything over will just spill out this way. So you can't just simply say, like, what's my biggest wall in each direction for my cell. It doesn't really work. Instead, what you have to do is you have to get, like, the whole container around your cell in some way. And this is actually a pretty tricky problem, to be honest. And the way this works is essentially we can just make a heap with the outside cells, because we know the outside cells won't hold any water because water can just spill out, like, here, right? So we can make a heap with all of these. So all of these, all of these, all of these. And then we can essentially start closing in the walls and keep track of, like, what's the smallest wall we've seen so far to get to our cell, and then that's going to be, like, the height we can get to. And then from there we can figure out, like, okay, what's the height it can get to, what's its height, and what's the extra, and that's going to be the water. So that part's pretty simple. Like, let's say a cell can get up to, like, 13, but its height's 8, so it can hold 5 water. If a cell can get up to 13, but its height's, like, 16, then it can't hold any water because it's already above that height. So essentially, that's how you can calculate that. So what we can do is we can say, like, okay, let's put all these numbers in a heap. And we know for sure that anything on the border will have 0 water. So we can make another grid like this. And we can just say, like, okay, all of these will hold 0. Now all we care about is this inner part. So for this inner part, now that we have a heap, we can essentially start popping the smallest wall first, and then we can put in, like, walls that it's next to, like a normal, like, path traversal, and then we can basically use that to know, like, what's the smallest height of this wall. So what's going to happen here is, like, let's say we pop this wall first. This wall, or not this wall, let's say we pop this cell first. This cell is next to it. So we can put in this cell into the heap, and the height to get to this cell is going to be 1, right? Because that was a 1. So here we're going to put in this into the heap with a height 1. And then also we're going to pop off this guy. And this is also going to be height 1. And now that these are done, then these two values are the same. So essentially we're going to have in our heap, we're going to have like the height, and then the XY coordinates. So essentially now we're going to pop off one of these. Doesn't matter which one. Let's say we pop off this guy. So now we're going to say, okay, so the maximum this can reach is 1. And it's already at 1. So this can't hold any water. So this will hold 0 water as well. So this cell will also hold 0. And then we can put in like the cells that are next to that cell. So this cell is already in our heap, so we can mark it like visited or whatever. Once we have a cell in our heap, we don't need to put it in again. So because this is in our, like these two were already in the heap. So this one we don't need to put in, but this one we do. And we're going to mark it with a height of 1 again. So essentially it got put into the heap with a height of, and what I mean is by the height of 1, I mean like the neighbor is going to have a height of 1. So this cell is going to have a height of 1. Yeah, and there's nothing else here. So now we pop one of these two because this is done. So essentially, it doesn't matter which one. So let's say we pop off this 8 first. So we pop this 8. And we know that the most it can hold is 1, but it's at height 8. So this is going to hold 0 as well. And then this is done. And now we put in this cell next because that's its neighbor. So this is also going to have height 1. And yeah, so this will be in our heap. So essentially you can see like none of these are going to be able to hold water because no matter what, the water is just going to flow out like here, 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 and so on. And so this is how you kind of like build a surrounding container and you close it in, closing in, closing in, by just always popping the smallest wall. And then that way, whenever you put a cell into the heap, it's basically going to tell you, okay, what's the height of my cell and what's the height of the smallest neighboring cell to it. And that's like my limiting factor of how much water I can have. And essentially you just do this with every cell and then you're done. And then, yeah. So honestly, kind of hard problem. The hardest part is figuring out like, how do I actually know how much water I hold? Because yeah, this is where I went wrong. I just said like, okay, let me just get the biggest wall on every side. And the smallest of those is going to be my thing. But like I showed you here, you can actually flow out like a different way. You don't have to flow like linearly. You can go in like some zigzag way to get out a smaller height. Yeah. And actually, I'm going to switch to Python from now on. I think it's just easier to understand, so focus on like algorithms, not language. So we just can do that. So essentially, let's take a look at it. Whoops. So basically, you just make the rows and columns, pretty standard. You make a visited set, you make heap, directions is all pretty standard. Then essentially, we're going to put in the top row and the bottom row. Let me actually clean this up. Go back. Okay, so we're going to put in the top row and the bottom row. And then for these, we want to make sure we don't like put in these cell twice. So we're just going to loop again to get these things. So this first loop will give me the top row and the bottom row. And then this will get the left and the right, excluding those corners. So we don't want to put those in twice. Put those into a heap and heapify. And it's more efficient generally. If you don't need to, if you're making a heap with a bunch of elements and you're not actually popping, it's more efficient to put everything in and then heapify, because this is O of n. Where if you kept putting stuff in, like a heap push, it would be n long n. So ideally, you just push everything in and then you heapify afterwards. And then while you have a heap, you basically pop off the height, the x and y coordinates. You get the new cell and you check, is it in bounds and have we not visited it? If we haven't visited it, we can mark it visited right away, because unlike Dijkstra's, we know for sure if we put in a cell into our heap with some neighbor height, we're never going to get that in with a smaller number. Like, it's not possible. So yeah, so we can mark it visited here. Sometimes it'll work either way. You can either mark it visited here or here. Doesn't really matter, but this will be more efficient essentially. And then yeah, basically calculate the water. So we can't have negative water. So essentially, I made yeah. So essentially, the water is basically like the height of its neighbor minus the height of the cell. So if there's something left over, put in some water. And if this is negative, then don't put in any water. Like let's say the shortest neighbor's height 1 and the cell's height 5. this will be -4, and you can't have -4 water. So essentially, water will be anywhere from 0 to a height difference. Add the water, and then what you're going to want to add is you're going to want to add the current cell's height, or the shortest neighbor, whichever one is smaller, because you basically want to keep track of like every cell I get to, what's the path I got there with the smallest height somewhere, and that's gonna be like the limiting factor there. And then yeah, just return. So yeah, I think it's kind of tricky, just like I said, because the figuring out like how to get this thing, on like how do I actually how do I determine how much water I have is kind of annoying. So the hardest part of it isn't like writing the algorithm, it's like how do I calculate the water correctly, I feel like. But yeah, so essentially this is going to be, and then yeah, I think I'll just stick to Python just because yeah, if I like doing this in Go has like interfaces with heaps, something hard to understand. I think Python's the easiest to understand, and if you want like Java or something, you can just put it into GPT and just convert to Java, and yeah. And also, if I'm going to be doing stuff live, Python's fastest. So, but yeah. So essentially, time. What are we doing? So we have the directions. This is nothing. We're putting in the outsides of the grid into our heap. So that's going to be like mn, or it's actually going to be m plus n technically. Yeah, so m plus n, but then we're going to be traversing every cell. We're going to be traversing every cell, but we're also pushing cells. So for every cell, we can put in like more cells. I'm not sure what's the biggest size of the heap we can grow to. Like, yeah, like I don't know if we can have mn space, but it's kind of hard to calculate because like we're popping a cell, we're putting in 4. I guess I'll say mn. So in that case, basically, what's going to happen here is this is going to be like mn log mn, and space will be mn. I guess for the visited set, this will definitely be mn, right? Because we're going to visit every single cell. So that'll be mn for sure. Time, yeah, I think it's going to be something like this, because essentially we're popping off a cell and putting in like two or three more every time, depending. I guess worst case we're popping off one, putting in like almost all of them. So then we're gonna have something like this, yeah. Let's see what this thing says. N, which is the matrix. Yeah, so I think n in this case refers to like the entire matrix, and I just said mn is like the width and the height and that and so on. So yeah, I can switch to Python. Let me know if you guys have any thoughts about that, just to make it easier to understand. Focus on the algorithms, not the language so much, and you can just convert to whatever you want. Yeah, so that's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.